So, linear approximation is using the tangent line to approximate values. So, the usefulness of this stems back to times before calculators, or parts of the usefulness of question 1, anyway. So, certainly, right now, we can type square root of 1.1 into the calculator. It's going to give us a very accurate approximation of what we have. But there was a time not very long ago, actually, in the grand scheme of human history, when no one could do that. So linear approximation is something that can be used to approximate values. So find the linear approximation to f of x equals square root of x at x equals 1. Use it to approximate the square root of 1.1. So f of x, if we graph it, it looks like this. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. And so this is what our graph of f of x looks like. So if we are limited to doing this without a calculator, then if I need to find square root of 1.1, I'm going to know it's going to be a little bit higher than 1, but I'm not going to be able to find a very accurate approximation. Yeah, so the idea of this is that if you find the line tangent at 1, because you can do that pretty easily without a calculator. So if we find this line tangent at 1, then my actual value, what I want to find is right here. Well, the tangent line value would be just barely more. They're going to be really close, right? So, so we're going to find a tangent line. To find a tangent line, we need a point. Ethan, put your computer away, please. All right. No, do not put those on. You do not need any more distractions. All right, so the point is f of 1, which would be the square root of 1, which just gives us 1. So our point that we're using is 1, 1. To find our slope, what do we have to find? The derivative. So this is, of course, x to the 1/2 power. So f prime of x is going to be 1/2 x to the negative 1/2. And I'm going to make that 1 over 2 root x there. We're all okay here. Questions, Thomas? You okay with the point? Just plug in the original for the point. Derivative, multiply up front by 1/2, decrease your exponent by 1 to get negative 1/2. Power rule. And then this is going to go back down to the bottom because it's got that negative exponent. And to the 1/2 power would be a root. Are you okay getting 1/2 x to the negative 1/2?
No.
Okay, so you're taking the derivative of the square root of x. That's your function. Square root of x is the same as x to the 1/2. Okay, so you just multiply out front by your exponent. So there's your 1/2. And then subtract 1 from your exponent. So 1/2 minus 1 gives you this negative 1/2.
Understood. So the x squared is the slope. You got to find the slope. You got the
So this is the original function. This is the function we're trying to find the tangent line to.
Okay, and then you've got to find the original function.
Right. And then we just move this back down. So this function gives us our slope at any point. Right, because it's our derivative. Derivative gives you slope at any point. I want to know the slope specifically at x equals 1 because that's where my tangent line is going to be. So now I'm just going to plug in 1 into that equation.
And how do you get the 1 over to the
So because this has a negative exponent, you're going to take it and move it back down to the bottom of the fraction so it goes down there with the 2. And then the to the 1/2 power is the same as a root. Okay? So whenever we plug in 1, we're just going to get 1/2 here. So there is the slope that I'm going to use. And so now I just write my equation of my tangent line. Ethan, put your computer away. Okay. Okay. All right. All right, so we'll have 1/2 x minus 1 plus 1, just plugging it into that point slope form. So that's our tangent line that we have here. Yes, Laura? Because this is an estimate right here, so you would have probably been okay, but my tangent line might not be drawn perfectly because I just kind of drew that in the way I was looking at it. So it is pretty good, isn't it? Pretty good tangent line I drew there. Yeah. So this is our tangent line. It is not going to give us the exact value for the square root of 1.1, but it's going to give us a close value when we plug in 1.1. Yes?
Can you label that y equation? Because I keep getting this.
Yes. Yes. So this equation right here, the black line, that is my y. That's
like the actual thing.
like label this as like a tangent line.
Y equals 1/2 x minus 1 plus 1.
So this is our tangent to f of x. Is that what you want to?
Yeah.
Okay.
Yeah. And what's the 1/2?
That's
the slope.
That's our slope.
Okay. And what's the 1?
The point. So we f of 1 equals 1, so our point 1, 1. Because we're using that point slope form, which is y equals m times x minus x1 plus y1.
Why can't we just write y equals mx plus b?
You can. The reason that we don't is because to do that it takes a few steps, and you might mess up on those steps. So, because if you were going to write that with y equals mx plus b, you don't have the y-intercept, so you'd have to work back to find the y-intercept. So if you use this, you just put everything in and leave it. You don't have to do any work for it. So this is your x1 right here, and this is your y1. So you just put this one goes right here, and this one goes right here. All right, so if we want to approximate the square root of 1.1, which is, I could also label this if I wanted to, that's f of 1.1. So we're looking for the square root of 1.1. It's not going to be exact, but we could approximate it by doing 1/2 of 1.1 minus 1 plus 1. And that would be 1/2 of 0.1 plus 1. 1/2 of 0.1 is 0.05. 0.05 plus 1. And then we'll get 1.05 for our approximation here. If we type it into the calculator, the square root of 1.1 is 1.0488. So it's pretty close. 2 decimal places in.
When you're solving that, to show that, do you need to carry your squiggly estimate equal signs down?
It wouldn't hurt. You actually could use those or an equal sign there because it's equal to the line before it. It's not equal to 1 square root of 1.1, but it is equal to the line that was before it. So, yeah, after this point. Technically, even if you put an equal sign the whole way, they're not going to count it wrong on the AP exam. Yeah, even if you put an equal sign, they still give it to you.
Oh, they do?
Yeah, if you get the right answer. Yeah, finding the equation of the tangent line at the closest point you could find it, and then plugging in that number. Yeah.
Isn't it basically like what we're doing with the overestimates and underestimates?
It is. It's the same as we were. So we've already done a lot of this, really. I think next time I need to just go ahead and teach this section in with that and leave it out of Unit 4. We did it with Unit 5. We've done it with some FRQ stuff, and it's kind of sprinkled in some of the stuff, mostly probably because 4 was supposed to be taught before 5, and so some of the stuff I gave you had some 4.6 stuff in it.
I kind of need a reword.
Yes. Okay. Alright, so this one doesn't, like, give you a function, but it asks you to approximate the square root of 8 using linear approximation. So what we can do is basically the same thing we did on the last one. We could say f of x equals the square root of x is our function that we're dealing with. What would be the closest point where we could actually do it without a calculator if we're looking for the square root of 8? Square root of 9, which is 3, right? So we could use x equals 9 to predict this, right? Because 9 would be our closest square root that we could actually find without a calculator. So I'm going to run through this fairly quickly because it's basically the same as the last problem, just at a different point. So f of 9 would just be the square root of 9, which is 3. So our point on the graph, our point of tangency is going to be 9, 3. We already found this derivative on the last problem, so I'm just going to, it'd be the same derivative, 1 over 2 square root of x. Right, so if we want to know the derivative at that point, we do f prime of 9. So I'd get 1 over 2 square root of 9, which would give me 1/6. That is my slope. Okay, here. All right, so next we need to do a tangent line. So, Thomas, what would the tangent line be?
1 over 6. X minus.
Good. All right. So, if we are going to estimate square root of 8 here, square root of 8, we would just plug 8 into this tangent line. So, we'll use a squiggly equal sign here because this is not exactly square root of 8, but it's going to be pretty close. So, I get 1/6 times -1 plus 3, so -1/6. Plus 3, and that is going to give us, let's see, that's going to be -1/6 plus 18 over 6. So I will get 17 over 6 for my approximation.
So that's positive. That wouldn't be an overestimate or underestimate. It needs to be squared. Or would it be overestimate?
Alright, so underestimate or overestimate has to do with the graph that you start with. So if your graph is concave down, like we see here, like the tangent line at 9 is going to be still above that graph. So this, basically for a square root, all of them are overestimates because you're always concave down for that. So this would be a slight overestimate. The actual square root of 8 is 2.82843, and 17 divided by 6 is 2.83 repeating. So you're a little bit over, but you know you're within it rounds to the same number to 2 decimal places. So it's pretty accurate. If you were in ancient times without a calculator, it would be pretty close to accurate for what you would need it for. As long as you don't need to be super precise. Yeah. It's not that long ago, really, that certainly that like calculators were not widely available. All right, so for those graphs are bad. I need to go back and put in Desmos graphs for them, but they're calculator graphs. But so like this graph was the square root of x here, and so if our tangent line is here, does the tangent line give you an overestimate or an underestimate, Ethan? Nope. The tangent line is that blue line. It is on top, so this is an overestimate. All right. We talked about it, yeah. All right, so if I have this graph, so this is the graph of sine, it looks like. All right, so let's look at this tangent line. All right, so do you have an overestimate or underestimate that's consistent? No. So what about if x is less than 0? Under estimate. Because our tangent line, our blue line, is below the actual graph. And then if I have x is greater than 0 for this one, that would be an overestimate. Just for this problem.
It's going on the wall.
Okay, so that x is less than 0, x is greater than 0 is only for this problem. But what is written below this is universal truth. So this you do want to accept as universal truth. If the graph is concave down, the estimate will be an overestimate. If the graph is concave up, the estimate will be an underestimate. So concavity, and I always just draw myself a picture. Like if something is concave down, right, the tangent line, no matter where it's at, it's got to be above that graph. If something is concave up, then your tangent lines anywhere are going to be below that graph. So I have to draw that picture for me to think about whether that tangent line's above or below most of the time.
What? Just answering. I've never seen that before. She's drew that like 8 times before.
It's connected now, though, right?
Oh, yeah, I understand.
Okay, good.
I've just never seen it.
Okay, we have the. Okay. All right. Okay. Okay. All right. Okay, we got a couple more to do. So for this particular function, we're supposed to use a linear approximation to approximate f of 2.1. Now this one you actually could do without a calculator, but it's going to take a little bit of work because you got to square a decimal and multiply. It'll take a little bit of work. Is it less work than doing the tangent line? Probably, but I didn't want to give you anything too awful here. So if we find f, we need to look at the point x equals 2 because that is our closest point where we could do this easily without having to get into decimals. So f of 2 would be 3 times 2 squared, 4 times 2. That's 2. So that's going to be 4 times 3 is 12 plus 8 minus 2, so we get 18. So 2, 18 is our point of tangent C. Now we need the derivative. So let's see, for that one, Ethan, what do we get for our derivative? Mm-hmm.
2 times 3 is 6, and then you get 2.
Subtract 1 from your exponent.
Okay. 6. Excellent. Plus 4. Amber's whispering 3 in my ear, and there's no 3.
All right. All right.
That is the derivative of that.
Right. Okay. So we're going to plug in 2. So 6 times 2 is going to be 12 plus 4, which is 16. That's our slope. All right. Quit. We got 9 minutes. All right. Y is going to equal, Emerson, what's our equation of our tangent line going to be?
16.
Perfect. Okay, here.
Yeah, I get that.
And so that is our tangent line at 2. We need to estimate f of 2.1. Label this whenever you plug in. It's f of 2.1. We need squiggly equal signs because this is not exactly the value, but it is close. So we'll have 16 times 2.1 minus 2. Thomas. So 1.6 plus 18, and we should get 19.6. Yes.
So how do we, this is easier than I thought. This is pretty easy. It's like somewhere over here.
Yep.
How do we do if it's an
All right, so this is a quadratic that opens this way. You could look at second derivative to tell for sure it is concave up, but we kind of know what this one looks like. So if this is concave up, and we're at 2, even though it really doesn't matter if we're at 2 because it's concave up everywhere, our tangent line would be below, so it's going to be an underestimate.
That's an underestimate.
Okay. No. Because if our graph was concave down, even though we use 2.1, it would still be, it would be, like it would not matter which side this one. Even if we used this to estimate 1.9, so it was like below, it's not going to work that way for these, because this will be underestimate even if you're plugging a number above or below that value.
As long as it's above the tangent line, it's an underestimate and below that.
Right. So concavity is the thing you want to think about.
How did you know that the graph looked like that?
I just knew this was a quadratic because it was x squared, and it doesn't have a negative in front of it, so I know it has to be some sort of U shape. If it's something you can't tell that with, you would take the second derivative, like the second derivative of this is 6, which is always positive. So since your second derivative is greater than 0, that tells you that you're concave up. Yeah. And sometimes it might be something that changes concavity, so you might have to plug in a number or something. Like you might have to plug in 2 and C. For this one, it was more simple, so you didn't have to. Okay? All right. Find the equation of the line tangent to f of x equals sine x at x equals 0. Use it to approximate sine of 2.5. Sine of 2.5, definitely not on the unit circle, something we cannot do without the calculator. So this is an instance where maybe they might ask us to do linear approximation with this. So f of 0 would be sine of 0, which we all know our unit circle so well that we can tell
It's 45.
me that that's not even close. No.
Is it 1? No, 0. No, sine is 0. Sine is y.
Sine is y coordinate. We're talking about this point right here. 1, 0, so y coordinate is 0. So sine of 0 is 0. No. 45-degree angle would be right here.
No, we could need an eye on this thing.
Right. I mean, like 55 times 7.
All right, so if we take our derivative, f prime of x for sine of x is just cosine of x. So if we find f prime of 0, that would be cosine of 0. What is cosine of 0? 1. There's our slope. So y equals 1 times x minus 0 plus 0. So basically y equals x. So I don't really love this one because when we're estimating sine of 2.5, it's just 2.5. So what you're doing is you're plugging in, like that is f of 2.5 is what you're estimating, right? Or equal sign. So it would just be x, which is 2.5. So you would estimate that it would be, hold on. That's not right.
Wait, so the sine of any degree is like...
This is not right.
Alright, you want to decide...
I think it just yields a bad estimate. Maybe.
Well, it's because you're plugging in 2.5.
Degrees is pretty close.
You're not even plugging in like 0.1, you're plugging in 2.5.
Yeah.
2.5 away from 0 on the sine line. Literally.
Yeah. Yeah, it's just a bad estimate. Not my favorite problem. Alright, so your assignment is on page 272. Let me make sure that's right. 272. One through 6, 39, 41, 50, 52. Yeah.